Hello, everybody. My name is Ozgur Sinanoglu. I'm with New York University, Abu Dhabi. And today I'll talk about logic locking in this special session. And in particular, I'll talk about metrics for logic locking. I'll talk about secure implementation. And most importantly, connecting to the theme of this conference, I'll talk about connections to VLSI testing concepts, testing versus logic locking. Let me acknowledge the sponsors of our research, DARPA, SRC, NSF, ARO, and Global Foundries. So as we all know, logic locking is an operation, is a transformation of a given netlist at either the gate or the RT level. A netlist it goes through an operation where we insert additional gates or we remove gates or we make modifications. And then at the end of this, we obtain a locked netlist that is different than the original netlist. It is this locked netlist that goes through the supply chain that we don't necessarily trust. And at the end of the chain, we obtain fabricated chips that has this locked netlist implemented in there. And this locked netlist has a circuitry that accepts a key, and only when the user or when some secure facility loads the key on the chip, then this chip is unlocked. That's the purpose of logic locking. So we call this operation unlocking or activation of the logic locked chips. So logic locking protects two different provides protection in two different forms. In the first form, as we can see, only the authorized users can make use of these chips, because if they load the correct key, the chips work. Otherwise, the chips will not be useful. So this is kind of a protection against overbuilding of chips by the fab, for example. Not every fabricated chip will be useful, and only after loading the key they will be useful. The other form of protection is against reverse engineering. So to understand what the chip does, to understand the functionality of the chip, you need to see the gate structure of any chip. And reverse engineering efforts have been shown to be successful in getting that, from gate structure to the functionality of the chip. But with logic locking in place, some of the functionality depends also on the key, the values of the key. These are zeros and ones that are to be loaded on a tamper-proof memory on the chip. So without the knowledge of the key, the attacker or whoever is trying to understand the functionality don't have the exact understanding of the functionality of the chip. So the key is needed, and this provides protection against reverse engineering. There have been different threat models defined for logic locking in terms of what the attacker has, what kind of capabilities the attacker has. In a simplistic threat model, we assume that the attacker has a functional chip, which is a logic lock chip, but it is functional. The key is in there, loaded already on the tamper-proof memory. So the chip is working, and the attacker can apply inputs to the chip, can look at the outputs, collect the outputs from the chip. The attacker can make use of the scan infrastructure, for example, to apply the inputs and collect the outputs of the chip. And from the applied inputs and collected outputs, which we call input-output pairs, the attacker tries to understand what the key must be. The typical attacker in this threat model scenario is the end user of the chip, who obtains the chip from the market and plays around with it. And the typical attacks that the attacker can apply based on the scheme is brute force, apply all possible inputs, or side channel analysis, look at certain characteristics of the chip, such as power consumption and timing. In a second threat model, this time what's available to the attacker is assumed to be a reverse engineered netlist, which is the locked netlist. So we see in this picture over here, we have this locked netlist that has 3 key gates driven by 3 key bits. So this is what's available to the attacker. And the attacker doesn't have a working chip in this threat model. So he or she is just looking at this netlist and trying to figure out what these key bits must be, K1, K2, and K3. So all sorts of netlist analysis the attacker can apply, probabilistic signal probability analysis, any sort of analysis. The goal is to understand the key bits from the netlist structure. The likely attacker in this case is the fab, the foundry, the untrusted foundry, because they have access to the layout files of the chip, which they can reverse engineer to get the gate level structure. And from there, they can do their analysis with the goal of identifying the key. And as I said, the approach is analyzing the netlist, the locked netlist. And the typical attacks in the literature have been in the form of removal attacks. Once you understand, so for example, you can isolate this key logic over here, you can remove them and hope that the rest of what you get after removing these gates matches what the original netlist was, which is often not the case. Oftentimes not the case. In a third threat model, this time we assume that both the locked netlist and the oracle, which is the working chip with the key inside, are available to the attacker. So the attacker does the netlist analysis, maybe does some simulation on this netlist. Of course, the key bits are not known, and the goal is to figure them out. But the attacker can identify what patterns to apply from the inputs, and then goes to the oracle, which is the working chip, applies those inputs, gets the response to them, and then based on this does some sort of an analysis based on the inputs and outputs to figure out what the keys must be. These attacks are called oracle guided attacks, and the famous ones are the first one, which is the sensitization attack from 2012, and the SAT attack from 2015. These are powerful attacks that have shown to break the earlier logic locking schemes when both pieces of information are available, the locked netlist as well as the working oracle. So based on these attacker capabilities and based on the three different threat models that we defined, what are the objectives of a logic locking scheme, or the defender? What are the defender's objectives? In the first scheme, when only the oracle is available, or when only the chip is available, then the idea is to make sure that that chip is as useless as possible for the attacker. So to make it as useless as possible, the logic locker can actually make sure that the chip fails in most of the outputs whenever they enter an incorrect key. So we call this output corruption objective, and this is effective for the first threat model. In the second threat model, where we have this time the reverse engineered locked netlist, but not the oracle, the attacker's approach, if you remember, was to analyze the netlist. So in this case, we need to make it difficult for the attacker to isolate and remove the key logic and obtain the original design, which is the intellectual property. So the things that the logic locking tool or person can do is the key logic can be intertwined with the original logic, making it difficult to isolate and remove. Or better, you can make some good modifications to the original design to obtain the modified design and implement that in our chip, which would make it very difficult for the attacker to obtain the original design from the modified one. We'll get more into this. And in the third threat model, where both pieces are available, the netlist and the oracle, we need to make sure that both output corruption and making the key logic difficult to isolate objectives are met, because we talked about them in the previous two threat models. In addition, we need to make sure that we give limited information to the attacker when they use the oracle to guide their attacks, such as the SAT attack and the sensitization attack. So these are the objectives. So for output corruption, for example, this is an easy objective to meet. What we need to do, what we can do, and this is what the earlier logic locking schemes had done when they were first proposed. We add some key gates controlled by key bits, and whenever the correct key is in place, it works fine for this pattern, for example. And when the key is incorrect, then the output fails. So we make sure that we fail the output for most of the incorrect keys, and that will get us good output corruption. This will get us good protection against overproduction of chips, etc. But then, as we know, attacks like SAT and sensitization can extract the key whenever the output corruption is too much. When the output corruption is too much, these attacks learn quickly about the incorrect key behavior with respect to the correct key behavior, and they can easily prune away the incorrect keys and obtain the correct keys. So the corruption is good to have, but too much of it is not. So what are the things that we can do for the IP protection objective? As we know, if we implement the original design on the chip as is, the layout files reveal the original functionality. The chip, when somebody opens it up and takes pictures, they can get to the gate level structures that will reveal the original functionality. So this is not a good idea. And that's where logic locking comes into the picture. We can modify the original design to obtain this new design called the logic locked design, or locked in particular here. And it's this locked netlist that is fabricated. So at the end, we have a chip that has something different than the original netlist. Of course, to make sure that this chip works as intended, which should give us the original functionality, we have some sort of a restore circuitry over here driven by a key that would undo the changes that we applied to the original netlist into the locked netlist. But this undoing operation is in the form of some sequence of zeros and ones being applied through the restore circuit to the locked netlist to obtain the original function back. This way we protect our IP, and depending on how we produce this locked design from the original design, we can resist these attacks, which we'll get into next. So, to sum up, what we've talked about so far is we need to modify our IP and then put it in silicon so that when somebody looks at the reverse engineered netlist, they can get clues about the original design. That's for removal attack resilience. And at the same time, we want some corruption, but not too much corruption, because too much corruption would lead to oracle-guided attacks being successful. So if this is our original function, this would represent a generic logic lock design where we modify the original function to get this purple block over here, and the restore circuit along with the correct key fixes the output by flipping the results for some of the inputs to get the original functionality back. The question that logic locking techniques need to answer is, how similar or how different do we want the original function and the modified function or the locked function to be? And how do we capture the similarity or difference? And why is this important? So error rate is a good metric to capture how similar or how different the original function and the modified functions are. And error rate is a good metric in the sense that we can quantify resilience to different classes of attacks, all in terms of error rate. So by just looking at this metric, we can actually talk about how resilient our logic locking scheme is to this attack, or to that attack, to SAT attack, to removal attacks, etc. So this is the right metric to look at. So what is error rate? That captures how similar the original function and the modified functions are, for example. Error rate is the number of input patterns, or rather the ratio of input patterns for which this block, original function, and this block, modified function, produce different results. Okay? So if we talk about like low error rate, then this means that the two functions are producing same results for most of the input patterns. Then this will give really limited information to SAT attacks, so that's good, will be resilient. But at the same time, because they're very similar, if somebody analyzes the netlist, they will get something very close to the original function. If they analyze this netlist from the locked chip, they will get something very close to the original function. And also, a chip that has an incorrect key loaded will work most of the time because the error rate is low. On the other hand, if we have a high error rate, then it will be good in the sense that modified function will be very different than the original function, so it will be resilient against removal attacks, netlist analysis attacks. The chips will be useless with the incorrect keys because it will be failing most of the time. The error rate is high. But at the same time, we'll be giving a lot of information to oracle-guided attacks, so SAT attacks will be powerful. But the bottom line is controlling the error rate helps us control the attack resilience. And that's what the logic locking technique should basically pay attention to. So we had proposed strip functionality logic locking based on this concept a few years back. And as we described, the locked netlist is obtained from the original netlist by making some changes. And we defined what the input patterns, the protected input patterns are. The protected input patterns are where the locked netlist produces a different output compared to the original netlist. So, and we showed that this kind of a scheme is resilient against a variety of attacks, but then there were some vulnerabilities discovered later on because the way we produced the locked netlist from the original netlist was based on relying on existing synthesis tools, which are not security aware, and they were basically revealing some clues about the changes that we were implementing on the original netlist to get the locked netlist. And as a result, locked netlist analysis would basically lead to the recovery of the original netlist. But nevertheless, this scheme, when implemented properly without relying on synthesis tools, can get us quantifiable protection because we can quantify the error rate and thus we can quantify resilience against a variety of attacks. Let's first talk about the error rate one more time. So the error rate in this example is 3 out of 8 because for 3 of the input patterns, the original and the locked netlist are producing different results. And when the correct key is in place, these differences are nullified by performing the flips for these input patterns, which we refer to as the protected input patterns. And when somebody puts in an incorrect key, then these flips occur on wrong positions, and then we don't get perfect recovery of the functionality. So correct key would work fine, incorrect key will not work fine. We see the differences for the protected input patterns. The different versions of SFLL that we proposed in the past was one based on looking at the Hamming distance characteristics. So the protected patterns were actually Hamming distance neighbors of the secret key. Or the user was flexible in the flex version to define what the protected input patterns should be. The user had the full flexibility for it. And in the third implementation, SFLL-fault, we were injecting a fault into the original design to obtain the locked design. And then the test patterns for the fault ended up being the secret key for this. Now, the first two implementations, as I mentioned earlier, rely on synthesis tools, and thus they had some vulnerabilities. But the last implementation, as I'll go into more detail, does not have this vulnerability. But more importantly, we see that the error rate can be quantified in terms of the parameters of the logic locking, which means by adjusting these parameters, you can adjust the error rate. And once you can control the error rate, you can have perfect control over resilience to attacks. You can talk about a certain resilience against brute force attacks. You can talk about a certain resilience against removal attacks. All in terms of, mostly in terms of error rate. And now we can control this error rate. You can talk about resilience against side attack and side channel attacks. Okay? So that SFLL is a logic locking scheme that gives you control over error rate and in turn gives you control over resilience against different classes of attacks. So let's revisit the objectives one more time before we get into the details of the logic locking scheme. We want to corrupt outputs, not too much, not too little. So we want to be able to adjust that level. We want the key logic to be difficult to isolate. We'd like to protect the IP, the original netlist IP. We don't want somebody to do the netlist analysis to figure out the original IP. And we want to provide limited information to oracle-guided attacks. These are the three objectives. So in SFLL-fault, the idea is to inject a fault into the original function And the modified function then becomes the original function with some gates removed based on this fault. For example, if you inject a stuck F fault, the vial will be stuck at 0. Whatever gate it's feeding, it's going to be either removed or replaced with a simpler gate. And then we keep applying this as long as those constant values are propagated. So the modified netlist will be a reduced version of the original design. So some gates are removed from the original design, which is good because when somebody analyzes the modified netlist, they will not be seeing those removed gates. Now, in this case, how do we recover the functionality from the modified function? Well, the test set, the test patterns of this fault that we injected need to be applied as keys to this modified design to recover the functionality, because that's where those are the protected input patterns in this case. The patterns in which the original function and the modified function produce different outputs, by definition, are the test patterns of the fault that we injected into the original function, as the testing community knows quite well. So then we can consult with an ATPG tool to tell us what fault to introduce into the original function, because the fault that we inject will determine the error rate, and we want the type of error rate that we'd like to get because we want certain resilience against all attacks. So we can choose the fault accordingly, and we can consult with the ATPG tool. So how do we do this fault injection? First of all, if you inject a fault over here, stuck at 0 fault, then in this case, what will be removed is this NOR gate, this inverter, and the modified netlist. We won't see those gates anymore. So if this is the original function, this will be the modified function or the locked function. And of course, there should be a restore circuit with a key, and the key over here will be the test patterns of this fault. So then we ask the ATPG tool, find us a fault with the right level of detectability, right? We have a certain target error rate. From this error rate, we can figure out how many carrier bits we want to see in the test pattern of that particular fault. So we ask the ATPG tool to find us a test pattern with that many carrier bits and not more. And that test pattern will then become the key for our logic locking. Now, of course, the fault may have other test patterns, and for those other test patterns other than T, we create and add this hardware in the form of ECOs into the locked designs, just to make sure that the locked design is different from the original design only for this test pattern T. That is the only protected input pattern. Looking at it from the attacker's point of view, if the error rate is small, then oracles will be almost useless because we give limited information to the oracle. If the error rate is large enough, then we're getting desired levels of corruption, so black box usage is not good either. And when it comes to netness analysis, what we're doing essentially is we're removing gates from the original circuit and obtaining this modified circuit. So the question is, can the attacker reconstruct the original circuit from the modified one where the gates have been removed? We claim they can't, because the gates have been removed. How will the attacker know what gates were removed and where they removed from, right? So this is we think that the attacker cannot do this. So we protect the IP that way. And then the SAT attack success, the approximate attack success, all are functions of the error rate. Removal attacks are thwarted because we're protecting the IP. So we have gone through a red teaming effort last year in 2019 as part of NYU's annual Cybersecurity Awareness Week activities. That 2019 edition was dedicated to a logic locking competition, and we acted as the blue team. We created some benchmarks protected by SFLL-fault as well as random logic locking. So there were 2 layers of defense implemented. There were 3 circuits, small, medium, and large, different key bit sizes, We also had a fourth circuit, a bonus circuit, a much larger circuit with a larger key. And we had more than 40 participants from 14 different universities. We had 18 teams altogether. We had judges from industry and government agencies. And the teams attacked our defense. We were the blue team, as I said. These were the teams that competed in the competition. And as we can see from these results, the random logic locking was broken by multiple teams, such as Carnegie Mellon, such as Northwestern. By the way, the notation over here is the team reports, for example, here that they broke 12 bits of the 40 bits, but when we check their results, they actually broke 4 bits of the 40 bits. So as we can see, random logic locking was broken by some teams completely, but SFLL-fault in particular, that's what we had in these circuits. None of the teams were able to break them, break the SFLL bits. The best was 4 out of 40 bits, 23 out of 60 bits, 0 out of 80 bits, and 8 out of 128 bits. And that was the UCSD team that took an effort. But SFLL-fault, our logic locking scheme still stands unbroken. So logic locking protects against a variety of different threats, such as unauthenticated use of chips, IP piracy, reverse engineering. We identify that error rate is the right metric to capture, because you can talk about resilience against different classes of attacks based on a function of error rate. We show that ATPG tools can actually be used to implement efficient logic locking for target error rate, and that's what SFLL-fault does, and that's what the connection to testing is. And finally, we not only validated this scheme based on theoretical security analysis, talking about resiliences and error rates, but also through a red teaming effort that I just mentioned. And we saw that SFLL-fault still remains unbroken. Thank you very much for listening.